Assalamu alaikum everyone. In this video, we're going to introduce you to a powerful mathematical weapon, the Laplace transform. We're going to show you what it is, why do we need it, and introduce you to the fundamental theorems of Laplace transform that will get you to solving complex problems in no time. Without any further delay, let's delve into the world of Laplace transforms. Okay, so first of all, we want to know that what is a Laplace transform and how do we see it. Okay, the definition of Laplace transform can be written like this. This is the Laplace transform symbol, and we can say that Laplace transform of any function that is in the time domain, the Laplace transform of any function that is in the time domain can be defined like this: the integral of 0 over infinity, that function multiplied by this operator. This is the actual definition of the Laplace transform. Okay, so now let's break this definition up into pieces. First of all, what is S? What the hell is S? Okay, so here S is nothing but a complex number. We all are familiar with complex numbers, I hope. So basically, S has a real part and an imaginary part. This is the real and this is the imaginary part. So basically, S is just a complex number which has a real part and an imaginary part. That's it. And so our definition looks something like this. Okay, so what is the purpose of this definition? We have transformed this time domain function into something else here using the Laplace transform. How did we transform it? All right, first of all, let's look at the right hand side of this equation. We have done some transformation of the actual function ft. What kind of transformation did we do? Look carefully here. Here is a function of ft and here is e to the power negative st, and we are integrating it with respect to t. So after we have finished the integration, then all the t's are going to get vanished because of the integration and because of the real limits here. All t are going to be vanished, and the only variable that's going to be left in this function is going to be the s right here. So we can say this function as capital F of s. So using Laplace transform, we took a function which was in the time domain, which had a variable t basically, and we transformed it into something in the frequency domain, which is a function of s, which only has the variable s. Okay, so we have transformed the actual function using the Laplace transform operation. And you might have noticed that I have said this is the function in the frequency domain. Now, why did I say that this function was in the frequency domain? Let's clarify that. Okay, so we have already discussed what S is. S is a complex number and it consists of a real part and an imaginary part. So why are we telling this as the frequency domain? We are telling this in a frequency domain because whenever we have e to the power st functions like this, so these sorts of functions are almost like this. So when s is equals to a plus bi, let's say, the real part and the imaginary part, both parts are positive, it creates a wave, or it creates a graphical motion like this. And when the real part becomes negative, then it creates a graph like this. It creates a graph like this, which increases with time. Okay, so this is when the s is negative, and this happens when the s is positive. So what does this signify? You see, this is a resemblance of a real wave in our everyday life. Why does this reflect a real wave in our daily lives? Because whenever we think of a wave, we think of like the sine wave with the constantly oscillating portions. We think of the cosine wave, which also has the constantly oscillating portions. But actual life, in real life, the waves are not without disturbance. There are disturbances in waves, and the waves decay and slowly stop. So this is a ideal scenario of waves which has no disturbance and they can progress infinitely. But these are scenarios of real-time waves which goes something like this. It starts, it oscillates, or it might not oscillate dependent upon the real part, and then it decays over time and eventually it stops. In order to determine the frequency of real-time waves, we need to be able to express them in functions like this, where s is a complex number and the real part and the imaginary part determines how the function will play out. Will it play out like this or that? So in case of real waves, the e power negative st, that resembles the situation of a real wave. To get a clearer understanding, let's say the wave we have s, a real part and an imaginary part, right? So the wave resembles this function resembles the actual wave. So what if we thought of a case where the real part is 0? Then the equation would be e to the power negative it times b, and we all know that e to the power negative it times b, that produces a circular motion like this. And we also know that the sine and the cosine wave, these waves can also be represented by circular motions, right? So these waves can also be represented by circular motions. So if we think that the real part becomes 0, if we take a case where the real part is 0, then we get this sort of scenario, which is a sort of scenario for an ideal wave, because we can express the ideal wave paths in circular motions. Okay, and also if we thought of another case where the imaginary part becomes 0, then it becomes a purely exponential function. So the mixture of these two. Okay, what does a purely exponential function do? A purely exponential function can do two things. It can decay over time, or it can increase over time. That's dependent on the value of a. If the value of a is negative, then it will increase over time. If the value of a is positive, then it will decay over time. So the mixture of these two cases, case number 1, which is a periodic motion for an ideal wave, and case number 2, which is an exponential function decaying or increasing, the mixture of these two cases results in the real wave resemblance. Okay, so that's why we're saying that we have transformed the time domain, a function in the time domain, into its frequency domain, where we can calculate the frequency using the complex number of s, because e to the power negative st creates wave-like resemblances. Okay, I hope you understood that much. Okay, so now we will come to the next question, that why are we interested in Laplace transform? Okay, so why are we particularly interested in Laplace transform? Well, we can think of Laplace transform like this. Any function which is in the time domain, if it contains many derivatives, if we have an expression which has multiple derivatives of this function, like let's say we were told to solve this equation. Well, this is an ordinary differential equation, and there are various ways to solve an ordinary differential equation which are really tiresome and lengthy sometimes. And let's say that you have been given a function of x and y, or you have been given a function, let's say that you have been given a higher order ordinary differential equations, or you have been given simultaneous differential equations, and you have been asked to find the solution of these simultaneous differential equations. It will be really tiresome and lengthy calculations that will lead to the solutions eventually, but using the Laplace transforms as a machine, we can take all these, the time domain functions, we can if we take the time domain function, then we can convert it into the frequency domain. We can convert it into the frequency domain if we take derivatives inside the machine of Laplace transform. The derivative becomes simply algebra, and that is one of the major advantages of using a tool like Laplace transform. So think of it as a tool. Laplace transform is nothing but a tool to convert derivatives and complex derivative equations into algebra, where you can easily simplify the equations and find the solutions. So these solutions and this determination of solutions can be easily determined by using the Laplace transform. So this is one of the fundamental reasons that we should learn Laplace transform for. Okay, so this is a brief introduction. Now we're going to delve into the properties, some properties of Laplace transforms. All right, before delving into the properties of Laplace transform, let us find some Laplace transforms of some common functions. For example, let's say we have a function which is 1, which is a constant, any constant. So, and we wish to find the Laplace transform of this function. Well, how would we find it? According to the definition, the Laplace transform of this function is going to be integral of 0 over infinity ft e to the power negative st dt. Okay, so if we can easily write that by actually inputting the value of the function, and then we're left with e to the power negative st dt. Okay, we can do something here. We can say that without doing the actual limits from 0 to infinity, we say that p tends to infinity and we are taking the upper limit as p. So this is going to be e to the power negative st dt, and we all know that e to the power negative st dt, the calculation is going to be negative e to the power negative st divided by negative s, and the limit is 0 to p. So we can say e to the power negative sp divided by negative s, or we can just take negative s common, 1 over negative s, and so we can say that e to the power negative sp minus 0, which is 1. E to the power 0 is equals to 1. So we get 1 by s, because we have limit p tends to infinity, which I forgot to write over here, limit p tends to infinity. So this is a historic moment for you, because we have just found the Laplace transform of a function where the function of t is equals to 1. So we can say that the Laplace transform of 1 is 1 over s. We can also find the Laplace transform of another simple function. We're not talking about properties yet. We're just finding some finding the Laplace transforms of some common functions. Let's say we have this function in hand and we wish to transform this function into the frequency domain. Oh, carefully pay attention here. We had a function in the time domain which was a constant, which is 1, but after we perform the Laplace transform, now it has become in the frequency domain, which has only s. Okay, so this is the function of s that we were talking about. Okay, so now if we try to find the Laplace transform of this function, this is going to be 0 to infinity, the same procedure. Okay, so now what can we do? We can do this. We know this operation, right? We can add the powers as the bases are the same. So from here we can take a minus common and we can save that, and now with the same limit we can say that the integral is going to be e to the power negative s minus a divided by negative s minus a, where the limit is 0 over p and limit p is tends to infinity. Okay, so now if we input the limits, then we will get the same result. We can take negative s minus a common and we can say that e to the power negative, there is going to be a t here, s minus a times p negative 1. So we get 1 divided by s minus a. So this is the function of fs that we were talking about. So we can conclude that Laplace transform of e power at is 1 divided by s minus a. So these are the Laplace transforms of some common functions. Okay, so now we can go over the properties of Laplace transforms. There are some general properties that are shown in the book at first, like the Laplace transform is linear. First of all, the first property that we can say about the Laplace transform, that it's linear. So if we have a Laplace transform of something like this, and we were asked to give the Laplace transform of this resultant function, then we can easily say that this is equals to this plus Laplace transform b times Laplace transform of g t. So this is the linearity property of the Laplace transform, and there are many other properties of the Laplace transform, like there is another property right here that we can, so this is another property of the Laplace transform. There are many other common general properties which can be understood very easily. If you go through the text, you can understand it really easily. So we're not talking about those properties. We're going to talk about some complex ones that students mostly fail to understand, that what are these properties talking about, or what are the significances of these properties. The first one that we're going to delve into is the Laplace transform of derivatives. Okay, so now we're going to talk about the Laplace transform of derivatives. First of all, let us introduce the theorem to you, and then we're going to prove the Laplace transform of derivatives theorem. Okay, so if Laplace transform of function of t is equals to function of s, we have done this from the general definition of the Laplace transform. We can say that Laplace transform of the derivative of a function, we can say it like this: s fs negative f0. Okay, so how did we come up with this stuff? Now we're going to prove it. Okay, so let's prove this formula. First of all, what do we know about the Laplace transform of derivatives? Okay, so how can we prove this property of the Laplace transforms? First of all, let's take the Laplace transform of derivatives. This, what will the Laplace transform of f prime t be? This is going to be integral over 0 to infinity to the power negative st dt. This is going to be the Laplace transform. Okay, so now if we use the UV method or the UV rule of integration by parts, then what do we get? We're going to use this as u and that one as v, the first one as v, the second one as u. So the expression is going to become, oh, before that we're going to do another thing. We're going to input this limit because we don't want to integrate over infinity direct. Okay, so if we do integration by parts here, then what becomes of the expression? The second expression, the expression after performing integration by part is going to be something like this. So e to the power negative st times ft dt. Those who don't remember the integration by parts, just a soft reminder for them. The integration by parts, if u and v are both functions of x, then we can say that u integration v dx is negative integration du dx integration v dx dx. So this is the formula of integration by parts, utilizing this formula here. Okay, so if we do du by dx, it's going to return negative s e to the power negative st. Integration of v dx, this leads to ft and dt. Okay, now if we input the limits here, and we always have to say that limit p tends to infinity, p tends to infinity. All right, so now if we plug in the upper limits and the lower limits of t here, then what do we get? Okay, this is what we get: limit p tends to infinity. Okay, negative, we get 0 over p, there is going to be a positive s e to the power minus st ft dt. Wait a second, this is actually the function, this is actually the definition of the Laplace transform of function of t, right? This is the actual definition of the Laplace transform of function of t. So we can easily say if function of t is fs, which we have stated in the beginning of our proof, then we can easily say this portion as fs times s. Okay, so this portion is sorted out, and what of this portion? E to the power negative sp. So this is going to be infinity, and this is e to the power negative infinity is equals to 0. So this is going to be 0, negative, this is going to be f of 0, positive s fs. So our right hand side equation becomes sfs negative s0, which is our answer. So we have proved the Laplace transform of derivatives, which is like this. Similarly, we can do the Laplace transform of double derivatives. If we do the Laplace transform of double derivatives like this, it's going to become s square fs negative f of 0 negative f dash of 0. Okay, there is going to be s multiplied here, I'm sorry. Okay, f dash 0. And very sincerely pay attention to the formula. This one, f0, this is the value of 0 in the time domain function. This is a small f0, not capital F0. These are two very different values, so we need to be careful that we input the value of the function in the time domain here. Okay, the frequency domain function is only here, we don't need to worry about that. Similarly, the frequency domain function is only here. These two functions are in the time domain functions, and then we have to process it, and we have to input those values in the time domain. Okay, all right, so now using the Laplace transform of derivatives, we're gonna find the Laplace transform of some very important functions, which is, okay, let's find the Laplace transform of sine at. All right, so if we figure that f of t is equals to sine at, then we know that f dash t, this is going to be a sine at. And we also know that f double dash t is going to be, this is going to be cosine at. And if we double derivative it, then it's going to be negative a square sine at. Okay, so now if we take the Laplace transform of the double derivative of this one, why are we taking the Laplace transform of the double derivative? Because we can express the double derivative as negative a square times ft. So if we take the Laplace of the double derivative of the function ft, then we can easily say it as negative a square times Laplace transform of f of t, and we are trying to find the Laplace transform of f of t. Okay, so that's the reason behind taking the Laplace transform of the double derivative. And we know a formula already about the double derivative of Laplace transforms, s square fs minus s times f of 0 negative f prime of 0. Okay, so s square fs, what does fs mean? Fs means the Laplace transform of ft, negative s times f0. So f0 is going to be 0, because we know that ft is sine t, so f0 is going to be 0, and f dash 0, so f dash 0 is cosine t. So if we input t is equals to 0 here, there is going to be a times 1, which is a, so there is going to be a negative a here. So we can say that this is equals to negative a square Laplace of ft. Okay, so now if we take Laplace ft common from both sides, then we are going to get negative a divided by negative a square negative s square. So we can get the result like this, and this is the Laplace transform of sine at. I hope you have understood it. Similarly, we can find the Laplace transform of cosine at, and that's going to be your homework. Okay, we can also find, okay, now using the Laplace transform of derivatives, we are also going to try and find the Laplace transform of another function, which is, we're going to try to find the Laplace transform of a sine hyperbolic at, that function. Okay, so we all know that if we take this as f of t as sine hyperbolic at, then f prime of t, this is going to be cosine of hyperbolic at times a, and f double prime t, this is going to be a square sine hyperbolic a times t. Okay, and if we take similarly in the same way, if we take the Laplace transform of f double prime t, we all know that this is going to be s square fs negative f0 times s minus f prime 0. Okay, so the Laplace transform of f prime t, we can easily say that this is equals to a square times ft. So we can say that Laplace transform of a square times f of t, and this is s square times Laplace transform of f of t minus s times f of 0. So if we input f of 0 here, we all know that the hyperbolic functions are e to the power x negative e to the power negative x divided by 2 for sine. So if we input x is equals to 0 or t is equals to 0 here, in this case f of 0 is going to be 0. So this is going to be 0 negative f prime 0 f prime 0. If we input 0 here, we know that for cosine this is like e to the power x plus e to the power minus x divided by 2. And now if we input x is equals to 0 here, or in this case t is equals to 0, then the function becomes 1. So this is going to be 1 times a, because there is an a multiplied here. Okay, so we can say that a square negative s square Laplace transform of function of t is equals to negative a. So we can easily say that the Laplace transform of the function of t is equals to a divided by negative a divided by a squared minus s squared. So we can say that a divided by s squared minus a squared, and that is the Laplace transform of sine hyperbolic of at. Okay, so in the same way you can easily find the Laplace transform of cos hyperbolic at, and that is up to you. Okay, so now we have finished the Laplace, the property of derivative. Okay, now we're going to find the Laplace transform of integrals. What happens when we try to find the Laplace transform of an integral? Okay, now we're trying to find the Laplace transform of integrals, and the theorem looks something like this. If the Laplace transform of function of t is equals to fs, which is our definition, we have already started like this while we were trying to find the Laplace transform of derivatives. So if the Laplace transform of ft is equals to fs, then we can say that the Laplace transform of 0 to t fu du, the function of the integral function, this is going to be fs divided by s. Now pay attention here. What does this signify? Okay, first of all, this is eventually gonna be a function of t when we input the upper limits and the lower limits in this integral. Okay, so this is actually a function of t in the end of the day. No need to be surprised by seeing the integrals and everything. So we can find the Laplace transform of integrals pretty easily. We need to find the actual Laplace transform of the actual function, which is here. And if we just divide the Laplace transform of that function divided by s, then we are going to get the Laplace transform of the integral of the function. Okay, let me prove the theorem first, and then we're going to look at some examples which will clarify this theorem even further. Okay, so let's try and prove this theorem, and we're going through all the proofs because they are important for your exams, and they can come, any proof can come in the examination, so you need to understand the proof of all the theorems. Okay, all right, now in the first step we're going to say that let the function of t that eventually fu was going to become, let that be g of t. Okay, so if we then differentiate the both parts of the equation with respect to t, then what do we get? We're going to get f of t minus f of t minus 0. I'm sorry, f of t minus 0. So we can get that g prime of t is going to become f of t, and we also need to find something else. We need to find the value of g of 0. If we try to find the value of g of 0, the integral becomes 0 over 0 fu du, which is eventually going to be 0 because the upper limit and the lower limit are the same. So g of 0 is equals to 0 and g dash of t is equals to f of t. I think you all have guessed that where am I going with these expressions that I have found. Yes, we're going to use the Laplace transform of derivatives to find the Laplace transform of integrals. So if we take the Laplace transform of g prime t, then what the expression becomes? The expression is going to become g, sorry, I'm really sorry, these are all going to be small letters. Actually, it doesn't matter. What matters is that you use distinct letters for the frequency domain and the time domain. So for the time domain, as I have used capital G here, for the frequency domain, I'm going to use a small g. So SGS negative g of 0. Okay. So the Laplace transform of g dash t is the same as the Laplace transform of ft, right? From this equation we can say, okay, so this is s times gs. Well, the Laplace transform of gs, or we can say that gs is the Laplace transform of gt. Okay, negative g0 is equals to 0. Okay, so the Laplace transform of ft is fs, and the Laplace transform of gt is integration 0 to t fu du. Isn't that correct? Because we have already defined the gt as the outcome of the integral of 0 over infinity fu du. So we can say that the Laplace transform of 0 over t fu du, this is going to be fs divided by s. And that's the answer. That is our proof. I hope you have understood that. Okay, so now what does this imply and how do we use it in case of various situations? First of all, let's say we take a question. Let's say that we have been asked to find the Laplace transform of this function right here. So how do we find the Laplace transform of integrals? Using this theorem right here. Okay, so if I wanted to use the Laplace transform of integrals theorem, we all know that integration of fu du, this is equals to fs divided by s. Okay, so the first step is we need to find fs. So what is fs? Fs is actually the Laplace transform of f of t, right? This is going to be small letter. I'm sorry, because I have denoted the frequency domain as capital letter. Okay, so fs is the Laplace transform of f of t. And what is f of t? F of t is going to be sine of 2t. And we have already known that the formula for sine at, the Laplace transform of sine at is a divided by s square divided by s square plus a square. So the value of a is 2, so it's going to be 2 over s square plus 4. So fs is this, and if we plug in the value of fs right here, we can say that the Laplace transform of this integral is this, and that's our answer. So using these theorems, we can easily solve many complex functions, and we can easily transform many complex time domain functions without any complexities in calculation. Okay, so that was our Laplace transform of integrals, and now we're going to talk about another theorem of Laplace transforms. Okay, so now we're going to talk about if a function has been multiplied with any power of t, how would we find the Laplace transform of that function? First of all, let us write the theorem first, and then we're going to try and prove it. So every theorem starts like this. If the Laplace transform of f of t is equals to f of s, then the Laplace transform of t to the power n f of t is going to be negative 1 whole to the power n d by ds dn dsn fs. So we have to multiply negative 1 whole to the power n, and we have to find the derivative, the nth derivative, the n being the power of t here, the nth derivative of the fs. So what is fs? Fs is the Laplace transform of the original function, the function that has been given here. So let's prove this theorem first, and then we are going to try and solve some examples using this theorem. These theorems are really important for finding Laplace transforms of various functions very effectively and efficiently, because Laplace transform calculation is all about efficiency. You don't want Laplace transform calculations itself to be very lengthy and complex, because you are using the Laplace transform as a means to simplify your equations. You are probably going to use Laplace transform mostly for the solving of differential equations. So Laplace transform is just a part of your whole answer. You don't want Laplace transforms to be very lengthy and complex. So that's the whole point of having all these theorems. Okay, so if we try and prove this theorem, how do we prove it? All right, so first of all, let's say that the Laplace transform of f of t, this is the integral of 0 over infinity e to the power negative st ft dt, and this is equals to fs. So now if we did something here, what can we do here? So in the right hand side of the theorem, notice here, we have been told to perform derivatives with respect to s, not with respect to t. Okay, so in our proof, if we perform derivatives with respect to t on both sides of this equation, and if we can prove that making a derivative here results in a multiplication of t here, then our proof is complete. Okay, it will my words will make more impact when we finish solving the proof. Okay, so what is our target? Our target is to differentiate both sides with respect to t. Okay, so if we differentiate both sides with respect to t, this one becomes df over ds. This is going to be 0 over infinity negative s e to the power negative st ft, so sorry, this is going to be negative t ft dt. Okay, so df over ds is equals to negative t with the Laplace transform of ft. Why didn't all the t portions and the whole integral didn't get affected? Because those are functions of t, and we are differentiating both sides with respect to s. I'm really sorry. We are differentiating both sides with respect to s, the frequency domain. So that's why all the integral and the functions of t, they didn't get involved. Only the e to the power st, this portion got involved because it has an s. All right, so differentiating both parts with respect to s results in this, and we can easily say that this is Laplace transform of t of ft, and we can take the negative 1 and we can take the negative 1 over there. So this is actually true for n is equals to 1. So we have proved this equation or this theorem right here for n is equals to 1, right? So because if we plug in n is equals to 1 here, then we get precisely this equation right here. But we want to prove it that this equation is true for all sorts of n. Okay, we want n to be any natural number, so we want to prove that this equation is true for all values of n. So how do we do that? We use a fancy mathematical technique called the mathematical induction. Okay, what does the mathematical induction tells us? We literally figure it out along the way. Let me not get technical at first. Let's just figure it out. Let's say for n is equals to k, we have this equation, negative 1 whole to the power k df over ds is equals to Laplace transform of t over k f of t. Because we have established that for n is equals to 1, this equation is valid. So if we plug in k instead of 1, the equations becomes like this. And now we're going to differentiate yet again with respect to t. So differentiating both sides with respect to s leads to negative 1 whole to the power k d square f by, so sorry, this is going to be k ds to the power k, and this is going to be d k plus 1 f divided by ds k plus 1 is equals to the Laplace transform of if we break it up, 0 over infinity t power k times negative t e to the power negative st dt. All right, so from here we get that negative 1 whole to the power k dk plus 1 ds k plus 1 f is equals to 0 over infinity t over k plus 1 times negative 1 e to the power negative st dt. So if we take this negative 1 over there, if we multiply both sides by negative 1, then we get negative 1 to the power k plus 1, and the k plus 1th derivative of f is equals to 0 over infinity. We can easily write it as Laplace transform of t power k plus 1 f of t, right? So this equation, the whole equation is true. This equation is also true for n is equals to k plus 1, right? So we have found that this equation is true for n is equals to k, n is equals to k plus 1, where k can be any number. So if k can be any number and this equation is true for both k and k plus 1, then mathematical induction says that this equation is going to be true for all n. Okay, so using this theorem we can solve problems where the function, the actual function in the time domain, has been multiplied by t or any power of t. So let's take a problem like that and solve it. So let's say that we have been told to find the Laplace transform of t times sine 80. So how do you find that Laplace transform? Okay, so we have already known that Laplace transform of t to the power n ft, that is equals to negative 1 to the power n, the nth derivative of fs. Okay, so first of all, let's find fs. What is fs? Fs is the Laplace transform of sine 80 here, right? So we have already known that the Laplace transform of sine 80 is a divided by s squared plus a squared. Okay, so if we want to find the Laplace transform of this one, so we can say that the Laplace transform of t sine 80, that is equals to negative 1 whole to the power 1 times d ds of a divided by s squared plus a squared, right? So negative dds of a divided by s squared plus a squared, that leads to a times negative 2 divided by s squared plus a squared whole square. There is going to be negative 1 here. So okay, and according to the chain rule, there is going to be dds of s squared, which is going to be 2s. So the result becomes twice as divided by s squared plus a squared whole squared. All right, so that's the Laplace transform of t times sine 80. So also you can find the Laplace transform of t squared cosine 80, let's say. You can also find that, so that's up to you. That's going to be the hw. So you're just going to have to do this negative 1 whole squared times cosine 80. The Laplace transform of cosine 80 is s divided by s squared plus a squared, so you just have to derivative this one twice, and in order to find the derivative of this one twice, you have to do the u divided by v method. You have to apply the u by v method and then find the result. All right, okay.